quantum gravity has left very few clues in the universe we see as to what form it takes. So places where we see a paradox are places where we have some angle by which we think if we can only understand this, we'll have learned something deep about the theory that we didn't have before. The reason I've got interested in this topic, given I'm not by any means a specialist in quantum gravity, is that I think there's a sort of communications gap. The string theory high energy community is in itself very convinced of these ideas. It's not doing a very good job of convincing people outside the field. Quantum gravity tends to turn up when gravitational fields get so strong that classical gravity can't handle them at all. That happens deep inside a black hole. But actually, and perhaps slightly surprisingly, on the horizon of a black hole, that's not a region where you'd expect quantum mechanics to matter. And it was a big surprise to discover indirectly through Stephen Hawking's work that quantum mechanics matters a lot around the edge of a black hole. He discovered that black holes really do radiate, they do emit light and heat, and they emit it at just the level you'd expect them to do if black holes were ordinary thermal systems. One of the things that Hawking noticed almost immediately in thinking about black hole radiation is that something funny happens when the black hole radiates away to nothing. What you expect to find is the space is just full of thermal radiation. I've got what you might call a sort of many-to-one evolution of the system. Many ways it could start, only one way it could finish. I can make the black hole in all of those different ways, but the thermal radiation left in empty space after it evaporates doesn't tell me how I made it. But physicists coming from a particle physics starting point, I think originally driven more or less by a hunch, but increasingly driven by sort of calculational arguments and evidence, came to think that the process whereby a black hole forms and evaporates again, that process should be describable in its entirety by the ordinary rules of quantum mechanics. And the ordinary rules of quantum mechanics are reversible, they're one-to-one. As a matter of mathematics, it should be possible to have a complete description of what's going on in empty space after the black hole evaporates, and then back infer the complete description of how the black hole formed. It ought to be the case that the radiation the black hole emits late in its life is very subtly correlated. The word we use in quantum mechanics is entangled with the radiation it's emitting early in its life. And the difficulty is that the Hawking calculation doesn't seem to give us that. The Hawking calculation, which is how we started to take all this stuff seriously in the first place, seems to tell us that the radiation is perfectly thermal, which is physics jargon for is information free, doesn't really tell you anything. The regime in which we're doing the calculations is one that we think we understand reasonably well, because, okay, again, black holes seem extreme by terrestrial standards, but the physics outside black holes, even very close to black holes, is not physics where we expect the really strange high energy features of quantum gravity to kick in. So the fact that we've got this apparent contradiction between two different ways of understanding the black hole radiation in a regime where we kind of think we ought to understand the black hole pretty well, that is really paradoxical, doesn't it? And that paradox probably is the route to realize why actually there's some important piece of the jigsaw we're missing. And if you're optimistic, it tells us that this is something we can leverage to get a really better understanding of black hole quantum gravity. If you're pessimistic, it makes us have a nasty feeling there's just something in the story we're not getting.